Welcome back to the Deep Dive. Our mission here, as always, is pretty simple. We take all the complex source material, the technical papers, the really fine-grained implementation notes, forum discussions, and we distill it all into something actionable for you.
Yeah, exactly.
Today, we are diving deep into the science of automatic speech recognition, ASR for short, and we're specifically focusing on what feels like a black art. Fine-tuning these huge models for your own highly personalized local use.
And, we really have to start this dive by acknowledging the ASR dark ages, because for anyone who's been in this space for more than, say, 5 years, you remember those painful, frustrating days we were running old HMM, GMM systems.
Hidden Markov models.
Gaussian mixture models, yeah, often on Linux. And then later, the early deep neural network systems.
I just remember them being perpetually disappointing. I mean, they required all these separate, really labor-intensive parts. You had to train an acoustic model just to recognize the sounds.
Right, just for the phones.
And then a totally separate language model to predict the next word.
Yeah.
And if you change your accent, or even just the topic you were talking about,
you had to re-engineer the whole thing. It was brittle.
Yeah, completely.
And the core metric we use, the word error rate, or WAY, which is, literally the percentage of words the system gets wrong. It was often hovering around 15, maybe 20%. It was a constant uphill battle.
It really was.
Then, September 2022, everything changed. Whisper was released.
That was a genuine watershed moment in the field.
It really was. I mean, Whisper just unified those clunky, separate models. It used a single encoder-decoder transformer architecture for both acoustics and language. And the critical part, it was trained on an unprecedented scale.
You're talking about 680,000 hours of audio.
680,000 hours of multilingual audio. And that massive training volume just made it incredibly robust to noise, super accurate across different accents, and it worked in over 98 languages right out of the box.
And that's what really took ASR from being this niche research topic to a commercially viable technology that just works.
Viable for general use, absolutely. But now we're at the next stage. So the question becomes, how do we move beyond just good general accuracy to, optimal personalized performance for your unique voice, your specific technical words, or the most complex thing of all, that mixed language code switching?
Right.
So our mission today is laser focused on that very first foundational step, data preparation. Because if you get the data volume wrong, or the quality is compromised, or the technical formatting is off, none of the fancy architectural tweaks in the world are going to save you.
Okay, so this is the blueprint.
This is the blueprint for your custom ASR foundation. We're defining the volume, the quality, that critical difference between clean and noisy data, the technical specs like chunking rules, and looking at the architecture that makes this whole small-scale personal fine-tuning thing actually work.
Okay, let's start with the central dilemma that I think a lot of people face. We have this behemoth, the state-of-the-art model whisperer, large V3, trained on what's basically decades of human conversation. And yet, here we are, suggesting that a solo user with maybe just 5 or 10 hours of their own voice should go and fine-tune a much smaller model, like Whisper Small. So is that personal voice adaptation, my accent, my code switching, is that a strong enough reason to bother?
It's not just a strong justification. It is, I would argue, increasingly the only way to get true excellence in these niche use cases.
Really?
Yeah. We have to understand that the stock large model is this magnificent generalist, right? But its huge capacity is spread pretty thin across 98 languages and countless different topics. Your 10 hours of your voice gives it hyper-specific context that is fundamentally more valuable for your personal accuracy than another 10,000 hours of generic YouTube audio.
That distinction is key then. The generalist versus the specialist.
It is everything.
So let's look at where that generalist model fails. You mentioned code switching, which is so common for anyone bilingual. If I'm switching fluently between, say, English and Hebrew in the middle of a sentence, what actually happens inside that stock Whisper model?
So when Whisper was trained, it learned language models mostly in isolation. It understands English patterns really well, and it understands Hebrew patterns really well.
But not mixed.
So when you introduce a sudden switch mid-sentence, like you say, I went to the Macolette to grab some milk, the model's language prediction mechanism basically goes into crisis mode.
Crisis mode, what does that look like?
It's a crisis because it doesn't have a high probability rule for an English sentence suddenly containing a specific Hebrew noun that is, phonetically unique to that language. So it often makes one of two mistakes.
Okay.
The first is it tries to force that Hebrew word into an English phonetic transcription. It tries to make it sound like an English word.
And you get nonsense.
You get a nonsensical word, or, even worse, a mistaken homophone. The other error is it just gets confused and momentarily shifts the entire transcription mode, and you get bad capitalization, messed up punctuation, and the flow is just broken. Your word error rate for that sentence just spikes.
So if I fine-tune it with just, say, 2 to 5 hours of my own mixed language speech,
you are providing a brand new, critical set of rules for the model's internal context. It learns that in your speech stream, Macaulay is a valid pattern. It should be kept as is, spelled correctly, and the English grammar should just pick right back up afterwards.
So you're defining your own linguistic conventions.
Exactly. You remove the ambiguity that makes the stock model's error rate go through the roof.
Okay, that makes sense. So beyond bilingualism, what about specialized technical vocabulary? I need to dictate code terms, PyTorch, gRPC, CUDA. The general model is going to choke on those, right?
Oh, absolutely. Technical terms bring in two really critical types of errors, rarity and homophone ambiguity.
Okay, break those down.
So even in a massive training corpus, the number of times a term like gRPC or a specific library name appears is just statistically tiny compared to common English words.
Right.
And then you have the homophone ambiguity. When the model hears the sound for cache, it's programming its entire history, tells it to predict the common word first, not the computer memory component, cache.
And you brought up the EUDA versus cooler example. That's all about context.
Precisely. If you're talking about software architecture, the probability you mean the GPU framework CEA is almost 100%, but the general model doesn't have that specific context. Fine-tuning solves this. It teaches the model your specialized vocabulary set, the required capitalization like the T in PyTorch, and most importantly, it resolves that homophone ambiguity based on the domain of your training data.
So it learns that when I speak, cache almost certainly means the technical term.
It does. It just eliminates those transcription mistakes and nails the spelling every time.
This brings us to what feels like the strategic aha moment here, the crossover effect. If Whisper Small has, by definition, a higher baseline error rate than Whisper Medium, how can specializing it actually make it competitive?
This is such a beautiful demonstration of specialization trumping generalization when you have limited resources. So the stock small model, it performs well across that massive 680,000 hours, but it has to make compromises. It just can't specialize deeply in any one area. But when you fine-tune it with your high-quality, specialized data, you are fundamentally redistributing the importance of its learned weights. You're reprioritizing what it knows.
So we're sacrificing its broad general knowledge for very targeted expertise.
Exactly that. The crossover effect means a fine-tuned Whisper Small model can actually approach, or in some cases even match, the accuracy of the stock, non-specialized Whisper Medium model, but specifically on your unique voice, your accent, and your vocabulary.
How is that possible?
Because the smaller model starts with a higher error rate, which means it has significantly more room to improve relative to its size.
I see.
We're basically forcing its limited parameters to get really, really efficient. We're telling the model, look, for this user, the probability of hearing the general word cache is now way lower than the technical term cache, so reallocate your bandwidth accordingly.
So the small model's initial weakness, its limited capacity, becomes its strength because it's forced to just focus its efforts.
That's the most concise way to put it, yes. We are trading the small model's high error rate in general stuff for its flexibility to become an expert in one thing.
And the practical result of that is huge.
It's immense. You get a really desirable level of accuracy, but you get the speed of the small model. Inference runs roughly twice as fast as medium. It uses less power, and it's perfect for fast, local, private, offline transcription on, normal consumer hardware. It's often the superior strategic choice for an individual user.
Okay, so moving from the why of fine-tuning to the actual ingredients, we've established data quality is paramount, which brings us to, I think, a core debate in the ASR community. Since my fine-tuned model is going to be used in real-world noisy conditions, a cafe, a busy office, shouldn't I be training it on recordings from those noisy places?
That is the most logical assumption, and it's also the one that leads to really poor training outcomes. The short answer is definitive. You must primarily record clean data and then add controlled programmatic noise augmentation.
Okay, so training on natively noisy data is a mistake.
It's inefficient, and it almost guarantees catastrophic overfitting.
Let's unpack the mechanics of that. Why does it fail when the whole point is for the model to be robust to noise?
Because the model has two totally different jobs to do. Job one is learning the signal. Your specific voice, your phonemes, your vocabulary patterns. Job two is learning noise robustness, the ability to pull that signal out of the chaos.
And if you train on noisy recordings, you're mixing those two jobs together.
You're confusing the objectives, and that leads directly to noise variability problems.
How so?
Well, when you record natively in a noisy place, the noise is inconsistent.
Right.
One recording has a specific traffic sound, the next has an air conditioner hum, the third has some cafe chatter.
It's random.
It's completely random. So your small 5 or 10 hour data set is now trying to learn hundreds of wildly different noise signatures at the same time it's trying to learn your voice. It just doesn't have the capacity to generalize from that. It might overfit to the hum of your specific office fan.
And then it performs worse everywhere else.
Exactly. It performs worse when you move to a different noisy environment.
And what about the signal masking problem you mentioned?
This is critical. Noise physically degrades the audio waveform. It literally masks the clean phonetic features that we want the model to learn. So if you train on degraded noisy audio, the model learns a degraded noisy representation of your voice. But when you use programmatic augmentation, you start with a pristine representation of your voice, the perfect clean signal, and then you systematically teach the model how to ignore the noise you add. The clean signal's core integrity is never compromised.
So the augmentation gives us control over the signal-to-noise ratio, the SNR.
Precise control. We can define the type of noise. Is it environmental, music, other people talking? And we can define the intensity. An SNR, 5 decibels, 10, 15. This systematic exposure, using massive pre-categorized noise libraries like MUSAN or AudioSet, builds genuine robustness. It's so much better than the random noise you capture natively.
This sounds like a lot of work, though. Let's get into the practical guidelines for collecting that primary pristine data. What kind of equipment and environment do you actually need?
The primary collection, which should be about 80% of your total data set, needs to be optimal quality. You need a quiet environment.
Not a sound booth, though.
No, not a professional sound booth. Just a room without major HVAC noise, traffic, or other constant sounds. And you need to use a dedicated quality microphone, like a USB cardioid mic. The Samson Q2U or the Blue Yeti are often recommended. They provide really high clarity without professional level costs.
And what are the technical specs for that clean recording?
You have to stick to the standard of 16 kilohertz sample rate or higher. And you have to save the files in a lossless format, so WAV or FLIC, to maintain integrity before the model ever sees them.
And the SNR?
Crucially, your clean recording must aim for an optimal signal-to-noise ratio of 30 to 40 dB. This just ensures the amplitude of your voice is significantly higher than any background hiss or rumble.
Okay, and you mentioned a supplementary 20%. Why do we need that?
That 20% is essential for adapting to device characteristics. If you plan to use your model for dictation on your phone or a specific laptop mic, you should record some of that 20% using those devices in their typical environments.
I see. So it learns the microphone's own fingerprint.
Exactly. It teaches the model the frequency response curve of that particular microphone, how its built-in filters color the sound. That's vital for robustness when you deploy on that specific hardware.
So once I have my, say, 10 hours of clean audio, how do I actually do the augmentation strategy?
You apply systematic transformations, so you're injecting noise from those corpora like MUSAN, adding background speech or music at different volumes. But crucially, you should also apply other signal transformations.
Like what?
Microphone simulation, which applies frequency filtering to mimic different recording devices. Reverb, to simulate different room acoustics, like a big conference room or a small office. And finally, subtle pitch and speed perturbations, speeding up the audio by 5%, slowing it down by 3%, just to make the model invariant to slight changes in your speaking pace.
So what's the recommended mix? What's a recipe for the best balance?
The consensus among ASR practitioners is a mix that looks something like this. About 40% original clean data, that's your bedrock 30% noise augmented, 15% microphone simulation or device characteristic training, 10% reverb and acoustic simulation, and maybe 5% for speed and pitch variations. That mix gives you a really robust model.
Okay, last thing in this section, let's nail down the volume. For our listener who wants to see real gains in code switching in technical terms, what's the minimum they need to invest?
For a noticeable improvement in vocabulary and accent, the practical minimum is 2 to 5 hours of high-quality targeted speech. That will give you a tangible relative word error rate reduction, usually in the range of 10 to 20%.
And just to clarify, a 20% relative reduction means if my WAR was 10%, it drops to 8%.
Exactly. And for solid domain adaptation, to make a true specialist model, we highly recommend aiming for 10 to 20 hours. That volume lets the model deeply encode your linguistic patterns, and it can really deliver a 20 to 40% relative WAR reduction.
And for production systems.
For large production efforts with multiple speakers, you're looking at 50 to 100 hours.
But the big caveat here is still quality over quantity.
Always. 10 hours of meticulously curated, high-quality, accurately transcribed, and properly augmented data is exponentially more valuable than 50 hours of messy, inconsistent, or poorly transcribed audio. It's, garbage in, garbage out. You cannot escape the fundamental importance of data quality in this process.
Okay, we've established the quality requirements. Now we have to talk about the hard technical constraints that Whisper imposes on the data, the format and size requirements that are, completely non-negotiable.
Right.
What are the core audio specs we absolutely cannot ignore?
So the Whisper architecture mandates specific standards that were set during its pre-training. First and foremost, the sample rate must be 16 kilohertz. This is a hard requirement.
What if I record at a higher rate?
If you record at, say, 44.1 kilohertz, the training scripts will downsample it, which is fine. But if you record below 16 kilohertz, the model is missing key high-frequency information that it was trained to expect, and performance will suffer.
In channels?
The model expects mono audio. If you feed it a stereo file, the system just averages the two channels. So for quality control, it's best practice to convert your audio to mono yourself beforehand.
Okay.
And we recommend 16-bit PCM for the bit depth, and as we said, always use WAV or FLAC for the format to keep the data pristine.
And what about final prep before you feed it into the model?
You need to clean up the edges. You should normalize the audio so the peak is between -3 and -1 dB. This just maximizes the signal. And crucially, use a tool to strip out long silences at the start and end of your clips. That's just wasted training time.
Now, let's tackle the great mystery of ASR architecture, the 30-second chunk limit. Why exactly is 30 seconds the absolute maximum? What's happening under the hood?
The 30-second constraint is just inherent to the transformer architecture of Whisper. It's tied to the fixed dimensions of the model's Mel spectrogram input. But more importantly, it's about the computational cost of the attention mechanism.
That's the famous ON constraint, right? The quadratic scaling.
That's the one. Exactly. For every single token in the sequence, every little piece of sound, the transformer attention has to compare it to every other token in that sequence to build context. So if your sequence length is n, the computation grows proportional to n squared.
Can you give us an analogy for that? Why does it get so bad?
Yeah, imagine you're at a party and you have to compare every guest to every other guest to see who knows who. If you have 10 people, that's 100 comparisons, 10 squared. If you double the party to 20 people, you don't just double the work. You quadruple it to 400 comparisons. For ASR, doubling the audio length from 30 seconds to 60 seconds would increase the memory and compute load by a factor of 4. It just becomes prohibitively expensive really fast. 30 seconds was the hard limit the engineers chose to balance context with practical efficiency.
So if I try to feed it a 45-second clip during fine-tuning, the script is just going to say no.
It's going to say no. It'll be truncated or more likely just rejected entirely. The architecture just cannot handle inputs that exceed that fixed dimension.
And what about shorter clips?
Shorter clips are fine. If your audio is, say, 15 seconds, it just gets padded with silence up to the 30-second mark. The model uses masking to ignore that padding, so it's computationally fine. You just can't go over the limit.
Okay, given that limit, what's the optimal chunk length for the data we're collecting? I find that dictating in conversational chunks is way easier than just isolated sentences.
And your preference is backed by best practice. We strongly recommend an optimal range of 10 to 30 seconds per chunk.
It's not shorter.
Well, single short sentences, less than 5 seconds, they're technically feasible, but they often lack the natural prosody, the flow, the contextual cues the model needs to learn fluent conversational speech.
Why is that natural flow so important?
Because the model isn't just learning to recognize isolated words. It's learning the rhythm of your speech, where you pause, how your voice carries context across phrases. A 20 to 30-second segment captures that density of information, which leads to much better performance when you eventually use the model for continuous dictation.
Plus, it's just more efficient to record that way.
Vastly more efficient for data curation.
Okay, so we have our audio chunks. Now we have to marry them perfectly with the transcription. I've seen on platforms like Hugging Face, the standard isn't just separate text files. They use this central wrapper file. Can you break down what that format is and why it's the standard?
Yeah, that centralized approach uses the Hugging Face dataset's audio format, and it usually relies on a central metadata file, typically a JSON or a CSV file, that acts as the single source of truth for the whole dataset.
What's JSON exactly?
It stands for JSON lines. So instead of one giant unwieldy JSON file, it's a text file where every single line is a complete self-contained JSON object.
And each line corresponds to one audio chunk.
Exactly. That JSON object on each line has all the metadata, the exact transcription, a speaker ID, the duration, and critically, a file path that just points to the actual audio file.
So why do that instead of just, matching file names? Why this whole system?
3 big reasons: scalability, integrity, and efficiency. First, integrity. It eliminates the fragility of relying on exact file name matching. If one file gets renamed by accident, your whole dataset is broken.
Right.
Second, scalability. This format enables lazy loading. The training script can quickly read all the metadata from that one JSON file without loading the actual audio bytes into memory until it's time for that specific training step. It saves a massive amount of RAM. It's just a robust, extensible format that's become the de facto standard.
This leads us right into the architectural paradox. We've defined the data, but how does our little 10-hour data set meaningfully change a model that was trained on 680,000 hours without causing catastrophic forwarding? It feels like trying to rewrite a massive library with a single new paragraph.
It does feel that way, but this is where the magic of modern transfer learning comes in. The first, and I'd say most important, defense against catastrophic forgetting is using significantly smaller learning rates during the fine-tuning.
Okay.
The original pre-training used a high learning rate to kind of aggressively explore the whole space of language and sound, but fine-tuning uses tiny rates like 1E5 or 1E4.
So what's the implication of that tiny learning rate?
Think of the model weights as thousands of little precision dials. Pre-training turned those dials aggressively to find the right initial settings. Fine-tuning just turns those dials a tiny, tiny bit.
Slight adjustment.
A very slight adjustment. We're ensuring that our new 10 hours of data only makes these minute, nuanced adjustments. It preserves the vast knowledge base while just subtly shifting the model's preferences toward your specialization. We update slowly so the new information doesn't just overwrite the old.
And the updates aren't even uniform across the whole model, right? You mentioned layer-wise learning dynamic.
Exactly. The model isn't treated as one big block. The updates are highly non-uniform. The very early encoder layers, the ones that learn universal acoustic features like basic frequencies and phonemes, they're barely touched.
Why is that?
Because your voice isn't so unique that it fundamentally changes the physics of how sound waves work.
Right, makes sense.
However, the later decoder layers, and especially the final output projection layer, that's where the model decides on the final word, the capitalization, the spelling, those receive the largest updates.
So we're not adjusting its fundamental understanding of sound. We're adjusting its interpretation and its output preferences.
That is the perfect way to put it. You are teaching it context-dependent preferences. For your voice, when it hears the sounds for cache, its preference style is now shifted strongly toward transcribing cache. The general knowledge is still there, but the domain-specific application of it is refined.
And for those who are really pushing the cutting edge, you mentioned lower low rank adaptation. How does that fit in?
LoRa takes this preservation idea to the absolute extreme. So instead of slightly modifying the massive pre-trained weight matrices,
which are millions of parameters,
LoRa freezes them completely. They're untouched. It then introduces these small auxiliary trainable matrices called adapter matrices right alongside the original weights.
So the original library is totally pristine.
It is untouchable, yes. We only train these small LoRa adapters, and these adapters are tiny, often less than 1% of the total model size, but they learn to capture all the new domain knowledge for your technical terms and your code switching.
And that's faster, more efficient.
Incredibly memory efficient, dramatically faster to train, and it absolutely guarantees the general knowledge is never damaged. If your fine-tuning workflow supports LoRa, it is the superior method.
Now, let's zoom out for a second and contrast our personalized fine-tuning with what the big players are doing. What's the difference between a solo user with 10 hours of data and, say, a major medical transcription service or an air traffic control system building ASR?
The difference is all about regulatory requirements and fault tolerance. Mission-critical operations do not use off-the-shelf, fine-tuned consumer models. They are embarking on multi-million-dollar, multi-year projects.
Right.
Their core goal isn't just high accuracy, it's regulatory-grade accuracy. They often need a word error rate below 5%, which is a colossal leap from consumer-grade performance.
And that requires completely custom solutions, I'm guessing.
Mandatory custom data collection is key, often hundreds of thousands of hours, because they need to capture really specific domain noise like the static and the jargon on ATC radio, or the precise medical terminology needed for HIPAA compliance.
So they build everything from the ground up.
They do. They rely on multi-model ensembles, where several ASR systems kind of vote on the final transcript, and they constantly use human-in-the-loop verification to manage continuous improvement. It's a completely different scale, all driven by liability and regulation.
That really clarifies the scope. Our goal is personalization and practicality, not 4.9's reliability.
Exactly.
Okay, moving to practical deployment for you, the learner, let's hit a major pain point. Running these models on AMD GPUs, which often struggle in an NVIDIA-centric world. What's the most reliable path for getting ROCm to work?
The landscape is definitely skewed toward NVIDIA's CUDA. If you have an AMD GPU and you want reliable performance, you have to use an inference engine built for portability and speed.
Yeah.
And the consensus Tier 1 option is Faster Whisper.
Why Faster Whisper over just the native PyTorch implementation?
Because Faster Whisper is built on the cTranslate 2 backend. cTranslate 2 is an optimized C++ inference engine. It's specifically designed for high performance and portability across multiple types of hardware, and it has excellent, well-maintained support for ROCm, which is AMD's equivalent to CUDA.
It is faster.
It offers inference speeds 3 to 4 times faster than the original PyTorch implementation. It's a huge boost.
So if I fine-tune my model in PyTorch, but I want to deploy it with Faster Whisper, what format am I converting it to?
When you convert your fine-tuned model for deployment, you should target that cTranslate 2 format for maximum GPU speed. But also, if you're planning for CPU only or edge deployment, you should convert to the GGOF format.
GGUF.
GGUF is the successor to the old GGML format, and it's quickly becoming the standard container for running these large models efficiently on consumer CPUs, often with far less RAM.
That's a critical workflow detail. Now, a common pitfall. When I'm monitoring my local deployment, I see my GPU utilization spike to 90, maybe 100% during transcription. Does that mean I have a massive bottleneck? Is my GPU too small?
This is one of the biggest and most costly misconceptions that people carry over from gaming or crypto mining. In AI inference, a GPU utilization spike to 90 or 100% during a processing burst is not a bottleneck, it is optimal.
It's what you want to see.
It's exactly what you want to say. It means you are using the compute power you paid for efficiently. ASR inference, unlike, say, rendering in a game, happens in these intense, short bursts. The GPU slams to 100% for maybe a second to process the audio chunk, and then it drops back to idle.
So that spike is good.
That spike is your friend. The metrics you should actually be monitoring are VRAM usage to make sure you don't run out of memory and temperature. If your VRAM and your temperature are stable, that 100% GPU utilization is a sign of a healthy, efficient system.
Finally, we talked about costs. For a user who's achieved this level of personalization, how does local deployment stack up against cloud services?
The savings are enormous. If you run your fine-tuned small model 24/7 on an existing desktop rig, the electrical cost is often negligible, maybe $15 to $30 a month.
Okay.
Now, contrast that with renting a comparable cloud GPU instance 247, which is typically going to cost you $250 to $500 or even more per month. For the individual specialist, local custom ASR is dramatically more cost-effective, and you get total privacy.
Okay, we have completed a really comprehensive deep dive here. We've moved from the foundational reasons for specialization all the way to the granular requirements of data prep and deployment. Let's just quickly summarize the absolute key takeaways for building your custom ASR system.
First, you have to embrace the strategy. Fine-tuning a small or tiny model is the optimal path for personal, specialized use. You get that medium-level accuracy with small model speed and all the benefits of local inference.
Second, the data mandate. Clean data first, then controlled programmatic augmentation. You aim for that 30-40 dBSNR for your clean corpus, and then you use noise, reverb, and mic simulation to build robustness in a controlled way.
Third, respect the technical constraints. 16 kilohertz mono audio is mandatory, and that 30-second chunk limit is an unshakable architectural reality. It's dictated by quadratic scaling. Use that 10-30-second chunk range to get the best conversational context.
And finally, optimize your deployment. For speed on pretty much any modern hardware, faster whisper using C-Translate 2 is the gold standard, and converting to GGUF is crucial if you're targeting CPU or the edge. And remember, 100% GPU utilization is a sign of efficiency, not a bottleneck.
So the final actionable recommendation for you is to proceed confidently with fine-tuning a small model on 5 to 10 hours of that high-quality augmented mixed language speech. It's the fastest, most effective way to unlock truly personalized, accurate, and fast STT performance.
Now, as we wrap up, we know we can fine-tune for custom terms and accents. But here is a truly provocative question that comes from the output of ASR. Punctuation. It's often the last step, and we all have our own unique, idiosyncratic written styles, our personal use of commas, dashes, or ellipses. So, is it possible to fine-tune an ASR model to adopt your specific punctuation style?
That is a wonderful challenge. You know, the integrated ASR model tries to deduce punctuation from audio prosody, from your pauses and your intonation, but often our verbal pauses don't strictly align with our formal written style.
Right.
You might use dashes heavily in your writing, but you pause the same way a person who uses commas does when speaking. The model is going to be confused.
So we're back to that signal versus noise problem, but this time it's with style.
Precisely. For capturing these deep stylistic preferences, trying to force the ASR model to learn it from inconsistent speech is suboptimal. The most practical and, I think, most effective solution is to use a standard fine-tuned ASR for the raw text, and then use a separate dedicated punctuation model that you fine-tune entirely on your written history, your old documents, your emails, your articles. That historical text provides the dense, accurate, stylistic data you need to capture your personal punctuation preferences far more effectively than relying on the fleeting rhythm of your voice.
Style, speed, and precision. That's the perfect combination for any specialized ASR project. Thank you for joining us on the Deep Dive.
Thank you.